All right, line V1, learn task 10. We're going to take a look at synchronous starter operation. Once again, we're dealing with a synchronous motor, which means that we are going to go and have a motor that is going to go and start with AC windings that are going to be having AC applied on the stator, and then we are going to go and apply a DC to our rotor field. And a couple of things that we just have to go and make ourselves aware of before we start anything. First of all, the motor itself does have a winding that is going to go and be on the rotor, which means that if that winding were left open during acceleration, okay, we have the amortisseur winding that's going to go and take care of our acceleration, but if we left that winding sitting open the way that it looks right now on this diagram here, we would go and have some major problems, because we would go and have this winding that would then be circulating through my AC fields that I'm going to go and have on the outside over here, picking up flux and then collapsing that back in. So we would get a massive amount of inductive kick. So we're going to go and need to have something that is going to go and manage the inductive kick. Typically what we place some sort of a resistance across any type of a field, which is then going to go and dissipate any of that inductive kick type of energy. We're going to go and see that inside here later on. We're also going to need to see that as we get closer and closer to our synchronous speed, that we're going to need to go in time so that we can just close in at the exact right second, so we can go and lock in what we have here for our field poles to what we have for our stator poles. Let's take a look at this thing. As we go through, we're going to examine it once again using the benefit of a timing diagram, which is just going to go and show instantaneous highs and lows. And I've got a timing diagram drawn over here on the right hand side. This one is different than most of the other timing diagrams that I've drawn for you this year, in that it's showing a sloped line. Normally we show a line that's going to be either higher or it's either going to be on or off for a higher or low. In this case, I've drawn this one representative on a slope to show that the value of voltage that it needs to go and hold in is going to be dropping. And it's going to be for our polarized field relay for the AC coil of that, which is going to be picking up a generated AC coming off of my rotor. We're going to see that dropping out until we hit a certain point, at which point we're going to go and apply our synchronization. Let's go through just our control circuit here to begin with, and then we're going to go and take a look at how that applies to our actual motor circuit. I'm going to start by just running power through as far as I have got components on my control circuit over here. And then I'm going to go and run power through as far as I've got it on my actual power circuit up top over there. And then I'm going to go and run power through as far as I've actually got it on my DC circuit, which is going to be down here at the bottom. Note we've got a DC supply that is going to be providing power. This ammeter over here is nothing more than an actual ammeter. Is designed to go and measure the amount of current we have going inside of our fields. We see that we're going to go and carry current through all the way up to there. We are also going to go and see that we will carry current through this relay over here continuously. So we've got continuous power on the DC of my polarized field relay, as well as I've got this field contactor, but we see that the field contactor has got an M contact on the inside of this thing that is going to go and be, at this point, dropped out. We have got an open inside there. So this is as far as my power carries inside of this circuit. Let's go through this control circuit. We're going to start by closing in our start. As soon as we close in start, we're going to be able to go and supply power through to my CR1, which is then going to go through a set of normally closed contacts on my overload relay and my out-of-step relay. Overloads are going to be monitoring my motor for too much current, for too much heat. My out-of-step is just going to be making sure that I don't accelerate for too long. That's this line that we see down here on the timing diagram, which is going to be a defined time that we are going to use from that, where it's just going to, as soon as there's current flowing through here, it's going to start timing, and if that current is still flowing at the end of the defined time, then it's going to go and change state. We'll examine that one in a minute in the operation as we see that right over here, but right now we're not going to go and play around with that one. We're just going to look at this control circuit. So we see that as soon as we provide power through my control circuit over here to my CR1, CR1 is then going to go and close its associated sets of contacts. As soon as CR1 closes its associated sets of contacts, it is then going to go and provide power through to my M, which is going to go and close its associated sets of contacts as well. So we're going to close that there. We are going to go and close this over here. We are going to go and close these over here. So all of that is going to get fired in by my M. We see that over here on this diagram over here where we see the start. As soon as we press the start, CR1 picks up instantly. M picks up pretty much instantly. It's right in line with the CR1. There's no defined time between those, which means that we are now going to go and apply power all the way through to our stator. Since we apply power through to that stator, what we're going to have happening, I should erase those lines there, or that whiteout I mean, what we're going to have happening is we're going to create this synchronous field. And the synchronous field is going to start whipping around the outside of my stator, and at the same time, my rotor is going to be at 0 RPM initially. If my rotor is at 0 RPM initially, that means that it is going to be getting lapped by the synchronous field that's going around the outside of this thing, which means that there's going to go and be a large amount of frequency that we will induce in the actual field coil itself. And because we are inducing that frequency inside of there, because we've got flux that's moving around, we're going to get voltage and we're going to go and get frequency. It is going to go and form another path that is going to go and be inside here. So the instant we apply power over here, we go and start to create a voltage and a frequency. It's an AC voltage and frequency, and we're going to go and draw that AC line with just one other color over here. I'm going to highlight over top of it in red, just because that's the only thing I kind of got available to me right now that's going to go stand out. But we would see that it would be going through here, and through here, and back up like that. So as soon as we go and apply this, once again, the power that gets applied to our stator, it is going to go and create a voltage and a frequency. We're just going to call that AC voltage. That's going to go and follow this path over here. Because I've got that AC that is traveling through this whole thing, this PFR relay is going to go and energize right now, which picks up my PFR AC coil. That's what we're seeing over here, which as soon as that PFR opens up, it is going to go and open this up over here. That's why we haven't dealt with this field contactor, because the instant that we apply the M, we create the frequency, which opens this at the same time as this one closes. So this field contactor, for all intents and purposes, never has yet received power. This one closed, but this one opened, or vice versa. So right now, what we are going to go and have is we are going to have this path for current. That is going to go and happen. Now, there is this reactor over here, and a reactor is nothing more than a coil that we are going to go and have. The purpose of a reactor is to go and block the AC, but to be able to go and pass the DC that I'm going to go and have through there. You should remember that a coil inside a DC is going to go and block just for 5 tau, and then after that, it's going to go and have allowed full value of current. It's going to act as a short circuit after that 5 tau when it has DC. However, on AC, it is always going to go and have an XL defined by 2 pi FL over here, which would be what we have right now. We've got this red path going, which means that we have got AC right now, which means that this thing has got XL, so it is acting as if it were some form of resistance. I'm going to draw it in right now just as a resistance that is caused by XL. Okay? So it's going to be operating in parallel to this one over here, and it's really just blocking that path that we have right now. So this is our instant of startup. So we have pressed the contact start, fired in the contact relay, fired in the main field coil, or the main contactor, which has applied power to my stator, which has right away induced a voltage in this rotor circuit, which is going to be going through this path over here. This is still closed, this field contactor, because as we defined before, we have never yet applied power to the field contactor coil. These two are always operating, in conjunction, so that one is locking out when the other one is closing in, etc. So right now, we're going to go and have this that's going to be happening. Now, we're going to go and get acceleration of our motor. So we're no longer going to be at 0 RPM. We're going to start to go and build our RPM. And as our RPM starts to go and build, that means that this rotor is traveling closer and closer to the value of my synchronous field, which means that the difference between the rate at which my rotor is getting lapped by the stator synchronous field is going to be going down, and therefore my AC volts and frequency are going to be dropping. We've seen this diagram before, which just defines the AC inside of a rotor. We see that the magnitude and the frequency, the length of time, is changing as this thing accelerates. And that's what we're seeing off of this polarized field relay over here on this sloped line right over here. We're seeing that we've got a magnitude of AC that is continuing to go and drop, and all of this is happening during our acceleration time. So during acceleration time, the polarized field relay is seeing less and less and less and less value of AC until eventually it is going to get to a point where the polarized field relay is no longer going to be able to go and hold in. It's just going to have an insufficient amount of AC volts because those AC volts have been dropping significantly. And when it drops out, it is going to go and fire in some other contacts. Let's go and take a look at what happens. So as soon as my PFR goes and drops out on this coil over here, it is going to go and drop out right over here, which is going to go and close this line over here. And we would see that we would now have DC that would go through my field contactor. We see that over here, my DC, when my PFR drops out, my field contactor goes high. As soon as my field contactor goes high, it's going to go and do a couple of things. First of all, it is going to go and apply DC right over here. That DC is going to go and follow through this route over here up to my rotor. It's going to travel back through this reactor. Remember that DC sees a reactor as being a short circuit, and it travels through like that. So right now we see that we've got this green path, this complete path, that is going and carrying DC through my actual rotor circuit. This is going to go and happen when this thing closes in, my field contactor closes in over here. It is also then going to go and drop out this path, which would have been active there just for a brief little instant while this was closing in. This would have been active, but then this field contactor set of contacts opens up, and as a result, it drops out this path over here, which leaves us really with just that path for my DC at this point. I'm going to go and have continuous DC that is going to be going through my rotor because I have brought this thing up, I have accelerated, and I've locked it in. So now I'm going to be operating in this section of the graph over here where I'm inside of my synchronous operation. We can get rid of this XL thing because we don't have any XL anymore. We're no longer tied to that AC. We're no longer inducing any AC because we know that this rotor is traveling at the same speed as what I've got for my synchronous field that's going around the outside of this one. So that's our operation in a nutshell. It'll continue operating until the point that we go and hit the stop button. Once we hit the stop button, we will go and drop out all of our control circuit. And when we drop out all of our control circuit, it is going to drop out all of our motor circuit. And when we drop out all of our motor circuit, it is going to go and drop out all of this circuit that we have over here. My field contactor is going to go drop out. This is going to go and drop out, and we're going to be back down to our initial de-energized state, which looked like this over here. So, one more time, just really, really quickly, now that we've gone through it in depth, our order of operation is going to go and be that we are going to go and fire in our start. As soon as we fire, let me just erase those over there. As soon as we go and fire in our start, we are going to go and energize the start circuit, which is also going to go and energize the M circuit. So we see all of that over here. We press the start. At that instant, we fire, we bring high the CR1, we bring high the motor set of contacts. Those two are going to be high, which means that we are going to go and close this, this, and this, as well as we are going to go and close this. And what we will do then is, just for a very brief second, we are going to go and see a little blip, maybe on the field contactor, but not long enough that we worry about it. But it's going to go and apply power to my stator. My stator is then going to go and build that AC path that we defined there before as going through this over here, which means that we are going to go and have this operation where this thing is going to go and pick up. It's going to be running that PFR. PFR is going to be sitting open over here. So we start running. My PFR is going to go and have a large value of AC that is going to be at a high frequency, but it's going to be dropping off like that we saw there before. As it drops off, it's going to taper down until it's no longer sufficient to go and hold in the coil, the magnetic coil. And at that point, this thing is going to go and open. And when it opens, the PFR over here, when it shuts down, it recloses this set of contacts, which is going to go and apply my DC onto it. When it applies that DC onto it, it closes those over there, which is going to go and fire my DC power through what we before had as an AC circuit. It is also going to go and open this one over here. And we end up at that energized state like that on my actual rotor. It's a complicated thing. You know, it really is very few sets of contacts. If you take a look at the timing diagram here, this thing's only got a couple of rows, right? We only see 7 rows that are going to be off of it. But it is going to be a complicated operation because we are sensing, we're reading our values of voltage and frequency off of this AC PFR relay. And as a result of us reading off of that, we're able to go and time in once we get up to about that 92 to 97%. Let's talk about this out-of-step relay again for a second. The out-of-step relay only starts to go and read currents. I'm just going to go back to my acceleration over here. We'll ignore all the rest of this, but when we are accelerating the motor, we know that our only path for current at that point would be to go through this, and that. And so we see that we are continuously going to go and be passing current through the out-of-step relay during the acceleration, right? We see that right over there. As a result, this out-of-step relay is going to be starting to go and heat up. It is designed to go and create just a little bit of heat, and it's got a set of contacts. Now, it takes a while for it to heat up far enough to go and kick those contacts. That's what we're seeing over here off this defined time. If my acceleration is shorter than my defined time, everything is going to be fine. You know, we're going to go and kick this thing into operation the way that we should. If, however, my acceleration were to be longer, I'm going to go and draw over top of what I have here. But if this acceleration were to be that long for us to get up to speed, you know, it could be caused by a defined load that's going to be way too high or something like that. If that were to go and happen, that this took longer than what the defined time was, it would go and time out, it would kick that open, and as soon as it would kick that open, it would open this set of contacts up top here, right, because that's what's related to, which would go and shut down the motors there just as a protection to make sure that we're not going into startup too long, because when we're in startup, the only thing that is carrying current is going to be those amortisseur windings, and those are going to be light-duty windings that are going to be built into the rotor that are just designed to go and start us up. Once we have the motor turning at our synchronous speed, we no longer have any AC that's going to be induced inside of that amortisseur. That's why we're able to go and kick this thing out. You know, why that we lose that pathway over there and we're no longer going to be sensing inside of there. If we do cause, create something that is going to be too much load that's going to go and pull this thing out of synchronization, what will happen is that our amortisseur winding is going to go and pick up. At that point, we would go and have my synchronous field, which would be traveling faster than the rotor, and therefore we would induce current into our amortisseur winding. It's going to act the same as we would inside of any other type of rotor circuit, which is really just going to go and bring us in back up to speed. It's going to give us motor effect to try to go and carry this in. The other thing that the amortisseur winding does is that if we've got a load that's attached, let's say we've got a pulley and a chain, we've got a really heavy weight, and that weight starts to go and, speed away, just accelerates via gravity, and this thing starts to pull too fast around over here, then what we are going to do is we're going to go and get a braking effect that the amortisseur winding is going to go and do as well. No matter what the disturbance is as far as our speed on the motor, remember we want to keep it at synchronous speed, but if for whatever reason I go either a little bit above because I got a load that's overdriving it, or if I go a little bit low because I have got a too much load that's going to be placed on there, either way it's going to go and give us the same sort of effect, and that effect would be that we would start to go and induce AC into that circuit once again, and as soon as we would go and induce that AC, we would be able to go and create a little bit of voltage off of that PFR, the AC coil over there. That little AC coil will allow us to go and pick back up out of here. Just would allow us to go and pull this thing back in to start operation. Let's go one more time back into the polarized field relay and what it actually is. We did define inside of the previous video there what the PFR was, that it was going to go and be a AC and DC consecutive device, where we are going to go and have the permeability of our magnetic core, we're going to go in effect, right? We can go and lock down all of these individual domains that are going to be inside here, the more DC current that I place through here, the more domains that I can go and lock down, and therefore the fewer remaining domains that I have for my AC to go into effect. And because they're going to be locked down directionally inside of, based upon what my DC is, I'm going to go and have an aiding effect in one direction for my AC, and I'm going to go and have an opposing effect in the opposite direction for my DC. What that will do is that means that we are going to go and have weaker magnetic field in one of these directions. Let's go and align our DC fields around through here. If I have got a DC field that is going through here, it's going to be coming back out like that. We're going to go and have magnetic lines of flux that are going to be going through there. We're going to go and have some magnetic lines of flux that are going to be going through there. We're going to go and have some magnetic lines of flux that are going to be going through there. And as long as my AC were to be aiding this, that the AC was going to be strengthening the DC field over here, we would be able to go and keep this armature, this little J bar, closed. Remember that the armature itself has got that spring that's trying to pull this thing open. But if I go and lose my AC, my AC is going to be in the opposite direction over here. So I'm once again going to go, that's a black marker there, let me change that. If I'm once again going to be carrying my DC through like this over here, and then I go and have my AC going in the same direction instead of these two fighting, because right now that's what we had, is we had the AC that was fighting the DC, and so as a result they decided, hey, let's not fight, let's pass those lines of flux around the outside over here where we can both agree, because this coil can use them going in that direction, and this coil can use them going in that direction, so it strengthened it in that direction. But right now, where now my AC is pulling out my DC, any of my DC lines now are going to get pulled through here. So they're no longer going to be getting pulled through this bar. And because that bar has got that spring pulling on it, it is going to try to pull open. And what we see is we see this magnetization graph that we have over here. They're showing us a couple of different things. AC-induced field current in coil B. They're showing us DC polarizing current in coil C, which is going to be underneath that. And then they're going to go and show us the resulting magnetic flux that we are going to go and have. And so what we really see off of this thing is we are going to go and have one of these where we are going to go and have a really strong flux where both of these are adding together. We see that where both of these are adding together in the bottom. And then we see we're going to go and have a weak flux for the other alternation. As the AC changes direction, we're going to get a weak flux. And this is really critical that we have got one direction that is going to be stronger than the other, because the stronger one, it's going to hold in on, and it's for sure going to drop out on whichever its weakest value is going to go and be in. So it's going to go and apply the exciter at that point, the relay establishes contact, and my motor snaps into that DC field. All right, let's go back one more time to the main diagram over here and take a look at a few more components that we have inside of here. Out-of-step relay, we already defined that the out-of-step relay is going to go and just heat anytime that we've got AC induced inside of my field. It is going to go and heat, and it is going to go and eventually be able to kick this thing out. That would just tell us if this thing is going to be going too slow. If we have got too much heat on the actual rotor itself, if we have too frequent of a starting duty, that is not going to be able to be monitored by this. You would be able to, if you wanted to, you could add another set of contacts into the control over here that would just be an off delay, a TR that we would go and have. If I wanted, I could add another TR into here, and I could just go and use a TR set of contacts over here, which is going to be normally opened, time to open. That is going to go and draw that in like that. What this would be able to do is this would be able to go and provide us with timing so that every time that we shut this motor off, there's always going to be a definite amount of time before this thing is going to be able to go and shut back on, or be turned back on. This would just allow us to go and regulate the starting duty cycle, because that amortisseur winding, once again, is just going to be small squirrel cage bars inside of there. It's not designed to carry a lot of current long term, so we don't want to be starting this thing many times over. The last thing that we also have on here is that when I do have my DC applied, so once the motor is up and running, I've got the field contactor over here. What I'm going to go and have is I'm going to go and have that DC that is going to be traveling through this circuit over here. And you'll note that when it does travel through that circuit, that it travels through this field rheostat over here. And as it travels through that field rheostat, we are able to go and control the magnitude, right? We can read it off the ammeter up top here, and we can go and adjust that with our field rheostat, which allows us to once again go and do all those wonderful things that we can normally do with our synchronous motor and with the rotor field. Primarily, it is going to allow us to go and adjust the power factor, right? If we overexcite the rotor, if we drop the resistance inside of here so that we can go and pass more current through here, we're going to be able to go and create a capacitive type of effect off of this motor, which can counteract any other inductive effects that we have on the rest of our circuitry. All right, that is it for our operation of the synchronous starter. It is going to take you probably about 5 or 6 times of going through it before you're really going to get comfortable with it, but that's just really what these are. It is a complicated set of controls because half of our controls are really going to be based off of induction inside of here, not just strictly off of timing the way that we like them.